general. Okay, so hi to everybody, and thank you for the previous talk, because they just did, you know, the introduction, and I have an answer to the question by Mike. You know, what about if you don't have air pits? So what do you have? So this, okay, so and we didn't synchronize. So I put the PDF here yesterday. So that's wonderful. So the idea is, if you want to explain turbulence, so one good view is that you have a collection, a family of attached eddies, okay, from the larger scales to the smaller scales. They coexist in a statistical sense. If you do statistics based on these objects, which are coherent structures, okay, then you can get under some constraint, you know, under shear stress, and then so you put the constraint, and then you get the, you know, first, second order statistics, okay. If you read Townsend book, then of course it's very clear that these are statistical objects. You can have many objects that have the same average. So nobody knows who they are, okay? And so the hunt for the for the objects, for the coherent structures began. And then the question is, are these conical eddies that you read, you know, in Townsend book? Are these lambda vortices which have nice properties if they have some inclination and so on? Or is it something else? And of course, the question is never settled, because, you know, if you have the same statistics, then it could be the right one, okay? And so the two questions, who are they? And then, of course, you find what you're looking for, no? Except if you write songs and you are the U2, then you never find what you're looking for. But, you know, you know, so how did they sustain? So this is, so, okay, so this attached eddies theory is a kinematic stuff. So you have a distribution of objects. You don't care why they are there and so on, but if they have the good properties, you have the good statistics. So the second question is dynamic. How do they sustain? Okay, and this was the hairpin question. So we have an idea. Okay, I will not talk about that. Okay, because we have 18 minutes now, and but the idea is that there is growing evidence, and then maybe Javier will agree, and then Wang will agree, and then many other guys will agree, but not everybody. We're just a minority, so I try to spread, you know, this belief, you know, so that you have a coexisting set of self-sustained processes, in the sense coherent vortices, they generate the streaks and so on, okay, and they live in the same turbulent boundary layer, and then but these are coherent, okay, so you have to see this process in an average sense, okay, it's not a temporal average, a statistical, a phase average sense, okay. Okay, I will not talk about that. Okay, so we have a summary of our belief, you know, in this paper. You can look at the reference, and when I say growing evidence, then okay, the papers are said there. Now I will because the organizer, they asked me, you have to talk about the resolvent. Okay, so let's talk about that. So I will zoom on this part of the actually, at the end is nice, because you know, you will see I have a new result, you know, because of that, because I have to. So most of the kinetic energy is created here in this phase of the process. So when you go and you do the statistics, you know, the kinetic energy, where is the power, the turbulent, the power, most of the energy in the turbulent flow, this will come from this part of the process. Okay, so be careful, because usually, okay, in many papers, you have this process now, 1988, Borger and Brosa, they call this mothers and daughters and so on. But essentially, the idea is here. Usually, this is good to explain transition to turbulence. It's good probably if you go near the wall, okay? But, you know, if you want to do this in a turbulent flow at larger scales, then this is like a statistical project. You have to do a process, you have to do averages, okay? It's not on instantaneous fields. You have to, this process is after you have done some ensemble average, okay? Okay, so let's talk about that. And then I have so I will re-explain you, so, but I will go fast because Jane did it, you know, wonderfully. What is that most people do, okay, to explain that, okay? So it's the resolvent analysis. So the usual way to do is you do the Reynolds decomposition. So you have the velocity field, then you have capital U. So I will go fast because it's already being explained. And U prime is the perturbation, okay? It's not a statistical object, okay? It's a snapshot at a given time. This is the fluctuation, okay? Then you do your maths, and then you have the equation for the perturbations. And then what you do, you put the nonlinear terms, okay? If you do the time average of that, these are the Reynolds stresses, okay? In F prime. F prime is the forcing term. And then you have this system. Okay, this system is exact. Now you just rewrote Navier-Stokes. Okay, and the linear terms, you just put this in F. And then you say, okay, the important part will be in L because it does amplify in a very selective way some structures. Okay, this is the essence. And then you go, an important stuff is that the linear operator is linearly stable. Okay, the turbulent mean flow, you compute the eigenvalues, is stable. Then you look not for the eigenfunction, and so you look for the forced response. So you go in the spectral space, and then you do your transfer function, and you call it resolvent, which it is. And then what? Then you compare to the statistical data, okay, that you have from the DNS or from the experiments. So the question is, okay, if I do that, is it good to predict the statistics? Okay, that's the question. It should be the question. Okay. If you do control, if you want something very deterministic, you can stop there. But if you want to explain something in turbulence, then you have to compare to the statistics. And so you go and you have the spectral cross correlation. So you take the velocity in spectral space. So it depends on the streamwise wave number, the distance from the wall, spanwise wave number, the frequency, and then you do a time average or an average. Okay. So this is the velocity correlation. And essentially, if you express U as a forced response, then you just can transform this and you say, okay, S, which is the velocity correlation, I can express it like the transfer function times P, which is the correlation of the forcing times H star. Okay, that's it. So if you know who is P, so if you know who is the correlation of the forcing, this is exact. So you get S. Okay. So the question is, I don't know what is the correlation of the forcing, because I can either model it, so I can build, what people, many people try to do is to build a theory explaining who is F prime. So okay, I will do triadic interaction or something else, or I do a model like André Cavalieri. So I will try. But the question is, if you come from the turbulent side, F prime is a second order in U. So the correlation of F prime with F prime is a fourth order correlation in velocity. Okay, so you have to go and model the fourth order correlation. So it's a closure problem. Okay, so you can close at order 4 and then you get the statistics at order 2. But many people say, come on, why don't you close at order 2? No, and then you have the QL theory or GQL or whatever. Okay, but let me say, okay, what is resolvent analysis? So the main idea is probably that I don't care who is the forcing, because anyway, this guy, H, will select whatever the forcing is. I will always select the same stuff, okay? So I can use that, and then I don't care about the forcing, essentially, okay? So this could be, so in that case, if you do that, you say, okay, the forcing is a noise, is white noise. It is delta correlated, okay, in space and in time, maybe, okay? But in space, it means, so I have white noise, I have forcing everywhere. And then the correlation of the forcing is the identity, and then I need some power spectral density in front, okay, that I can fit to the DNS data, for instance, or I can have from some nonlinear theory, okay? So the question is, does it work? If you do that, of course, this is very nice, because if this is true, P equal identity times P, then the correlation of the velocity is equal to a scalar constant times H star. So if you do the eigenvalues, eigenfunction of that, you call the spectral POD modes, which are the eigenfunction, the Carrur and Loewe modes in the spectral domain, the correlation of the velocities. But if I have the resolvent and I do the eigenfunction of H star, I call this resolvent modes. Okay, so the two theories are the same. You get the same truncation and so on. But then you get, if you do that, then you compare who is the dominating one, the second one, and so on. So let us compare the operators without doing the decompositions. Okay, let's just, I don't decompose. I just take these operators. And then I do a plot. Of course, this is a multidimensional space. So let me compare the streamwise velocity, power spectral density in spectral space, which is a function of the wall normal direction and the frequency, so the phase speed. I can talk about phase speed. For a given alpha and beta, okay? So I give the wave numbers. So for instance, I select the wave numbers of the near wall cycle. So I have a spanwise wave number 100 wall units, and then I have the streamwise wave number 450. This is the peak in the pre-multiplied spectra. And then I get the power spectral density of the streamwise velocity. So these are DNS data. This has been done by Pierluigi Mora with the Swedish code by Dan and so on. So it's the Reynolds tau is 1000. Okay, so I begin to have some scale separation. Okay, otherwise, Okay, so I go near the wall, and then this is what everybody knows. So this is the power spectral density. This is the phase speed. This is the wall normal distance. The new wall cycle has a maximum of streamwise kinetic energy of streamwise velocity around the 15 wall units. And then because the maximum is at 15 wall units, it travels at the speed there. Okay, this line is the, this is a wall, this is a velocity, then you can put the mean flow, and it travels at 10 C plus equal 10. This is what everybody knows. This is DNS. Can I reproduce that with the resolvent? Okay, if I use white noise forcing, and the answer is not. Okay, so if you, this is the, okay, your p-tot normalization. What does it mean? It means that I assume that the noise is white also in time. So I give the same energy everywhere. So I just put the total energy here, which is a constant that I give it to the resolvent. Okay, operate estimation. And then actually the maximum is in the center of the channel. This is what you found, yeah, no? So you don't see it. You don't see this. So if you just use the mean flow velocity in the analysis, in the resolvent analysis, you're not able to reproduce what happens near the wall. You need a second, okay? Because you give a velocity, you also need a time scale or something else to get, okay? You don't get it. Now, let me say, okay, but the forcing is not white in time. It has some color, I would say Mikhailo. So let me give the color in time, okay, the P of omega, like in the DNS, okay? It means I normalize the energy for every phase speed. So if I do that, I improve stuff, okay, because I normalize, but still, it goes, to the center of the chart. Okay, now I do this for two other wavelengths. So the other wavelengths, which are larger scale motions, and then I spare you what happens in the log layer. But if I go to larger scale motions, so alpha and beta, I give it. So the spanwise wavelength 1.5 H, the streamwise wavelength is 3. And then this is the DNS, okay? So you see you have the maximum at 0.5 roughly of the larger scale modes. But then if you try to do this with the resolvent, it's better, but it's very concentrated near the, okay? It's like a critical area. So the maximum is very high, okay? So most of the energy has a very high peak because, okay, you have less support to have it. And then if you normalize like that, it's better, okay? So it's good, but maybe we can do better. And why? And of course, this has been explained many times, because of course, the forcing is not one noise in space, because you have coherent structures. So if you assume that it is a white noise, which is delta correlated, this is wrong, because the coherent structures induce some correlation in the forcing. So in U prime times the gradient of U prime, like everybody knows. So what should we do? And the idea, I want to advertise a nice paper, 50 years old, but still, good, by Reynolds and Hussain. So this was exactly what they tackled. And the idea is, okay, if you have your U prime of your equation, you should divide it in two parts. The first that you obtain by phase average. So this is the coherent part, okay? The stuff that prevents P from being a white noise, and then everything else, the residual motion. And then you derive an equation for U tilde, okay? The coherent part of the motion. But then you have the nonlinear terms in the forcing, which are like U second time U second correlated, okay? So this is the transfer of energy to the small scales. This is the interaction between the larger scale streaks and the near wall cycle, not that Ivan does, and you can quantify. And then the idea is that you have all the other scales. So I can do triad interaction, but then this is a continuous energy transfer to a continuum of scales. But people know how to deal with that. It's called eddy viscosity. Okay, or you can do something else more sophisticated. It is the transfer of energy. Okay, this is the nonlinear term. Okay, so this model is like before. You have a linear operator, the turbulent mean flow, but then you have this eddy viscosity. And what it is the nonlinear term. Okay, this is U second time U second. But now there is a model in which by an eddy viscosity, I put it in the linear operator. Okay, this is called the any Newtonian model, and then is a model, is a closure. But then it's not so bad, okay? The message of today, this is not so bad, okay? So if you do that, you have a new linear operator. Now you include this part, and then, okay, then you have the U tilde like that, and then you do the resolvent, and does it work? And the idea is that now I put, okay, essentially the forcing now is white noise in space. Okay, I do what before didn't work. Now I do it again, because I say, okay, the residual noise, I don't care. And this is what you get. So this is the near wall structures. This is the DNS data. This is the resolvent with the eddy viscosity without any, okay, with white noise in time. I can improve it if I do white noise in space. Okay, this is power spectral density. These are the larger scale functions. This is the DNS like before. This is if you don't normalize, because one noise, okay, it's like if you're forcing with a larger scale up to the wall, which of course is not, you should put some wall function, but if you normalize properly, or if you put some wall function, you get that, okay? So this is very nice. And then, so let me do this partial summary, okay, but then it will be a 15-minute talk, no? Yeah, why not? Okay, so you have the quasi-laminar approach, is the approach without the eddy viscosity. It's nice if you have P. So you should use that if you know who is the forcing. So if you do a nonlinear theory, or if you know what it is, or if you do statistics, that's nice. If you don't know who is the forcing and you don't want to put any model, and then you take white noise, please don't use the quasi-laminar approach, because of course you will build on something that does not an accurate near-wall cycle. Then in that case, just add this eddy viscosity, which is a way to include the nonlinear transfer of energy to the smaller scales with something that scales how it should, okay, in the log layer and so on. Use this Reynolds cosine 72, okay? And then it has, you have a good estimation of the correlations. And then I will not show you that you can prove also that it has the right scalings, okay? It's a self-similar, okay? So the resolvent modes are self-similar in the log layer. You got the scaling with the Spain-West wave number, they come out by hand, okay, from the resolvent. Yeah? And I will, but this, okay, you can take a look at this paper, otherwise I will be too long. But then I want to spend the last maybe 6 minutes, 6 minutes to say, okay, this is what I wanted to present. And then thanks to the organizer, so I went on back to the to the result and say, but come on, I know what the discussion will be. Okay, you will say, this is nice, but then we want to do the forcing and so on, and then and that's it. Okay, so and the discussion will be, everybody will go along this way. So, but now let me go on. Okay, so imagine that I add a new parameter in the problem. Okay, so this is the forced response. I have a stable linear operator. So I compute the response to the forcing. Otherwise, everything will go to 0. Okay. Now let's add another parameter, a control parameter like the Rayleigh number. Okay. Begin to hit the walls, and then I have this linear operator that becomes unstable. Okay. I can, and then I want to compute the unstable mode, the critical threshold. Who's the best operator? Quasi-laminar or the other one with the eddy viscosity in a turbulent flow? Okay, I want to do a linear instability of a coherent structure in the turbulent flow. This would be Kelvin-Helmholtz coherent vortices, von Karman coherent wakes, Rayleigh-Benard rolls, okay, in the turbulent atmospheric boundary layer and so on. Okay, so let me do this analysis again. Okay, and then I was amazed. You will see this is okay. So I take a turbulent channel like before, Reynolds tau very high, but now I had a second parameter, Rayleigh number, because I hit the bottom wall and I cool on the top, so I have the delta, the difference. Or you can, consider the Richardson number, okay, which is like the Rayleigh number. And then you have this plane. So there are, okay, so this is the Reynolds number. We were here is a pseudo log plane. So what we were discussing is in this region, when the Rayleigh number is equal to 0, you have global stability. But now you can increase the Rayleigh number, and you can increase the Rayleigh number at I Reynolds number. Okay, so you have a turbulent flow and you begin to hit. And then what happens? And then the DNS, the nice DNS by Sergio Pirozzoli and his group in Rome, Roberto Verzic and so on. This is what they see. So if you are at 0 Rayleigh number, you get, this is the temperature field in the half channel, okay? So you have this turbulent fluctuation of the temperature field, okay? Now you increase the Rayleigh number, okay? And you see this. Okay, if you do go to the snapshots, you can discuss, you have the plumes, they go up, this is unstable, but on average, okay, nothing changes. If you do, this is the forced convection regime, and then the statistics of the mean flow. So the temperature is a passive scalar in that case, okay? But now what happens if you increase the Rayleigh number? So if you go, so in the green situation, this is a Richardson number 10 to the minus 3, but if you go to 10 to the minus 2, you see this, bang. Then you have these coherent rolls, okay? Instantaneously, they look noisy, but if you do the time average, so these are something like Rayleigh-Benard rolls. So the question is, can I predict that with a linear stability analysis? And which operator should I use? Okay, so what should I do? And essentially, I repeat the analysis before, like before. Sorry, I forgot. Yeah, you have tilde everywhere. They are the coherent motions. You have the same linear operator as before. You have the eddy viscosity. Now you have the buoyancy term. And you have an additional equation for the coherent temperature fluctuations. Okay. And then in this analysis, again, you need just the mean flow. So the input is, you know, the mean flow. You need the mean temperature gradient. And then you can derive by conservation, know who is the eddy viscosity. Okay, they should be consistent with the mean flow. Okay, just by conservation of momentum and of energy. So you just need capital U, capital theta. Then you put it in inside that, and you get, and you have the parameter is a Richardson tau. And then you compute the eigenvalues of this operator. I have no forcing term. Okay, so you cannot invoke, I have to put stuff in the force. Okay, and then, and that's it. So I have, you know, these dots here is where in the DNS you observe the coherent roles, a sufficiently high Rayleigh number. These empty circles is where in the DNS you have no coherent roles. And then this is the critical curve that you compute with a Prandtl equal to 1. You compute it with this linear operator, okay? So Reynolds cosine is good. Is it just in the middle? So thank you to the organizer, because I didn't believe, you know, it was almost suspect. It's just in between. Okay, if I do the quasi-laminar approach, imagine, okay, let's take the case where I am, the Reynolds number is 10 to the power 4. I have no rolls at where the Rayleigh number is 10 to the power 5. I have rolls in the DNS when, so not me, is Pirozzo et al. In the DNS. I have rolls when this is 10 to the power 6. What I just show you is that the critical Rayleigh number is a 647, so it's in between 10 to the power 5. But if I do the quasi-laminar approach, I have our critical Rayleigh number, which is 10 to the power 3. It's almost like the laminar Rayleigh-Bénard instability. Okay, so it's completely off. It's off the scale. Okay, and then it has nothing to do with F or P. It is L. Is the linear operator. Okay. So conclusions. First, most of the energy in turbulent flows, when you go to high Reynolds number, is in the large scales. Okay, this you know. You also know, so convection rolls, large scale streaks, and so on. So it's a problem. How can we compute that? They are non-universal structures. So whatever you do, you will have not a theory, like for the small scales. Okay, so you have to do the computation each time, which is what you do in linear stability analysis. Okay, you get a different mode and different stuff. So this you will have to do case by case. Okay, to do that, you can use linear stability analysis. So the main message is it does work. Okay, it does work well, but you need to model the small scale, larger scale interaction. So let's say the universal part, you know, the one at small scales, you must have a model. Okay, you can try to put it also in the linear stability analysis. Maybe the task is too big. Okay, you can use what already exists and then just go and build on top of that. You can use weakly nonlinear theories and so on, like has been done to do transition, but now on the turbulent flows. That's the big, you know, the big picture. But you need to put some model of the residual motion. Then the second advertising is 50 years after, this model is nice, eddy Newtonian model. Of course, it does work because this instability, I just show you the streaks, or they have omega equal to 0, so they are not oscillating structures. They are very large scales because the Strindberg scale is infinite, and then they're very large scales. If you want to go at smaller scale, then you have to improve the model. So the Reynolds cosine will not work. You have to find something else. LES, okay, you have models, okay? But if you would do channel flows, this is good because it's good to give you the resolvent when the flow is stable. It's good to, okay, have an instability. And then another stuff is that this is a statistical approach. Okay, so the idea is that when I look for U tilde is an average, is a statistical average, a phase average. You can do LES, this would be the resolved field, because you do averaging in a near, okay, in space. If you do an average just in one spatial direction, you will get something like that. So it is a statistical analysis in which you do a closure of the second order correlations. Okay, and of course, much of this work has been done with other guys, you know, Jung Wong, Ashley Willis with the resolvent, Pierluigi Moore, Onofrio Semero, and Dan Henningson for the DNS of the resolvent. Okay, thank you very much.
Thank you. We in the furthest. Thank you, Carlo. Really nice work, and the results for the as you know, we've done similar thing for the jet. It looks very,
I know, yeah,
look,
yeah, I know.
looks quite similar. You know, the paper has 500 citations since 2018, so we don't really need another one. So that's okay. But I do want to, in all seriousness, I want to have a little debate here about the triple decomposition, right? So the triple decomposition only sort of notionally informs what you're doing here, right? Which is that you're breaking the fluctuations into two separate pieces, and you're then computing an eddy viscosity for one based on the sort of total mean flow eddy viscosity, right? So for the benefit of the audience, you know, we need to understand that that's not self-consistent. There's no there's no self-consistent way of deriving that equation. That's point one. And point two is that it's misleading to think of it as the triple decomposition per se, because the triple decomposition is posed with a phase average on the first term. And in a natural turbulent flow, there is no natural phase reference from which one can compute a phase average. So you've done the statistics correctly in your work, but it's not fair to attribute that to the triple decomposition, which is based on a phase average. Right.
No, okay, so the big question is, what should you use?
Don't work.
How do you do this average to have U tilde? This is your question. Okay.
This is a
question,
LES. This is a question for
no. I give you the answer. For instance, an LES. So for instance, okay. So if I do an LES, I do a local average. I have to be careful with the, you know, the fact that the average does not commute. And so, but then, okay, okay, my U tilde is the resolved field.
It's fine. You can define it how you like, but the problem is that the properties of everything else depend on how you define those statistics. So if you define the statistics,
I agree.
If you define the statistics according to LES, then none of your residual structures have the statistics that you're showing here.
I agree with you.
It has to be self-consistent, is the point.
Yes, but okay.
I'm sorry if I'm formulating this like a critique of you. It's more.
No. But I like the discussion. The scope here is to discuss. So the. Okay.
Yeah.
But can I just? No. So because it's just will be short. The main point is that somewhere, if you want to do these, you know, larger scale covariance structures, you have to put a closure on the small scales. And then all the closure we know, otherwise we would have, there will be no meeting, okay? Because we would have solved turbulence. So whatever closure you choose, it will have some drawbacks, okay? So but the message here is, even if you take eddy viscosity and everybody will tell you, this is isotropic, it's completely wrong. And then if you go to Christos Vassilikos, you tell, no, what do you, okay? So the message is, even if I take a poor model, it does work not too bad. This is the main message I give.
I agree.
Okay, so the discussion. Yeah.
Okay, very nice talk, and you might know what I will ask. So the eddy viscosity value, was it the Ran's averaged value, or was it much smaller as it would be needed if you do triple decomposition? So basically, what value of viscosity, this eddy viscosity you use?
This eddy, okay, you're asking about the model I use, but this is in the Reynolds sign paper. So this is called the Newtonian eddy model. It goes back to Lamley. No, it's, you know, and then they know, you know, they knew that it is not perfect and so on. But, you know, Javier did the computation. It's the full eddy viscosity.
Full eddy viscosity. Why? Because now when you introduce tildes, right, you removed part of the Reynolds stresses, and therefore you should reduce the viscosity.
Yeah. But
that's we discussed this, but okay,
we can discuss.
I got it. This nice comparison was done with high eddy viscosity, full one.
Now, what I would like to specify, if you give me the mean flow and I use this model, which is the Newton, I have no free parameters. I just compute the eddy viscosity corresponding to the mean flow, and I assume that the U tilde are small and they will not change the eddy viscosity. Okay, so this is the main assumption, and then it's wrong, like all assumptions. You know, they're never satisfied, but it does work. So the measure, even, you know, even if it is imprecise and so on, it does work well.
One problem, Sergey, is unless you use the full eddy viscosity, your profile changes.
Yeah.
And then you have an stability on a changing profile. But we have a couple of short questions.
Yeah, but
We
No,
should
but-
have a couple of short
it's not me.
Tiny question or comment.
Yeah, go
You
on.
mentioned that the mean profile used in L should
Sorry?
have. You mentioned that the mean profile used in L
Yeah.
should mean that L should be stable, but actually that's not true. There's nothing in the formulation that requires it. You just need the eigenvalues not to be on the imaginary axis. And a counterexample would be an inclined square cylinder where we were looking at shedding frequency. You
We
just
have to
have an
discuss that,
unstable
but
mean profile. There's no
I don't
reason
know.
why. it
When I
has to
was
be
a kid,
stable.
they told me that when you have an unstable linear operator, then you know the homogeneous part of the response is the dominating one.
Yeah,
So when you're stable, then is a forced response.
but you have a nonlinearity. So
Okay.
So the thing saturates, and when you take the Fourier transform at the beginning, you're basically assuming your system doesn't blow up. So you
should
never
do
excite
Laplace
that
transform.
space.
Yeah,
Or
we can discuss.
well,
Yeah.
it can be stable.
Last question.
Another one.
I just want to ask, how did you sensitize the eddy viscosity to buoyancy?
How did I put this, the eddy viscosity in the buoyancy?
Yeah, how do you sensitize it to buoyancy? So buoyancy does something to the, does it do anything to your eddy, your model
Okay,
for the
this
eddy
is the
viscosity?
good question. So the idea is the mean profile I take is the mean profile in the forced convection regime. You know, if you do stability analysis, you take Poisson flow, and then you ask if it is stable or not, or you know and then when it is stable, you don't take the mean flow because it has been changed by the instability. So when I do the stability analysis, I take the mean profiles before the onset of the convection.
Okay. So let's thank the speaker again.